We request all the participants to
network issue.
mute
We will be
to
starting.
remain muted.
Good morning, everyone. Good morning, sir. Sir, we'll start in a bit. We'll start with inauguration.
Good morning, Sandeepan.
Good morning, sir. Good morning, everybody.
Good morning, everyone. It gives me immense pleasure to welcome you all to the online FDP program on probabilistic machine learning and deep learning for engineering and business, organized by Electronics and ICT Academy, MNIT Jaipur. Over the next 5 days, this intensive 40-hour program will offer a unique blend of theory and hands-on practice, led by eminent experts from IITs, NIT, and other esteemed institutions. This FDP is a vital step toward empowering educators, researchers, and professionals with cutting-edge knowledge in probabilistic approach to machine learning and deep learning, aligned with national visions of Digital India, Make in India, and NEP 2020. We are truly delighted to welcome such a diverse and enthusiastic group of participants from across academia and industry. Let us all make the most of this opportunity to learn, collaborate, and grow together. We now proceed further with the virtual lighting of the ceremonial lamp, symbolizing the dispelling of darkness through knowledge, the beginning of a new academic journey, and the collective spirit of learning and enlightenment that this FDP embodies. We would also like to take a moment to express our deep gratitude to Professor N.P. Padhi, Director of MNIT Jaipur and Chairman EICT, for his unwavering support and visionary leadership. His consistent encouragement and belief in the power of capacity building have been instrumental in shaping initiatives like Faculty Development Program. We are especially thankful to him for continuously inspiring efforts that enhance the academic and professional growth of educators and researchers across the country. Now I have the honor of inviting a visionary academic leader and the guiding force behind EICT Academy, Professor Vineet Sahula, Chief Investigator of EICT Academy and Professor in Department of Electronics and Communication Engineering at MNIT Jaipur. Professor Sahula currently serves as Dean, Digital Infrastructure and Services at MNIT Jaipur and holds a PhD in VLSI Design, an MTech from IIT Delhi, and a BE from MNIT, his alma mater. His research span hardware, resilience, security, EDA for
Thanks, Dr.
VLSI,
Shinu. Thanks.
embedded
I think we can
systems,
go ahead
and
and
cognitive architectures. A strong proponent of secure and reliable hardware, he combines academic excellence with visionary leadership. Professor Sahula has consistently contributed to advancing technology, education, and research with depth and integrity. His leadership in the EICT Academy has significantly shaped capacity building program across India. We are truly honored to have you with us. May I now request you to kindly address the gathering and formally inaugurate the program.
yeah, thank you, Dr.
Over to
Shinu.
you, sir. Vinit sir.
Yeah, it's my pleasure to be here with all of you. Dr. Sandeepan, Dr. Devesh, my other faculty colleagues, Dr. Gunjan, all participants, students, volunteers, and my academy staff there. I think this is really a happy situation where Dr. Sandeepan has chosen to present the mathematical background based kind of insightful, you can say, interactive sessions to understand the significance of machine learning. This is, I think, a rare program, and I congratulate Sandeepan and his really put hard in making this feasible under the auspices of academies. At Academy, I just want to present to all of you that we are just humble facilitators. All coordinators work hard. Thanks to all the speakers and experts who have kindly consented, and the participants who have joined here with enthusiasm. I hope we stand good at their expectations from the program that way. So I again welcome you all, and please go ahead with such a program. I wish I could attend few more sessions. Thank you very much, and wish you all the best. Over to you, Dr. Shinu. Maybe on part of Dr. Shinu, I can invite Dr. Nanda to say something about academy activities of academy. If he's there, join there. Dr. Nanda is coordinator of AICT Academy Center and co-investigator of this funded project by Ministry of Electronics and IT.
Thank you, Vinit sir, for giving me an opportunity to speak on this particular program. I hope I am audible to.
Yes,
Yeah,
sir.
you are audible.
Yeah. So this program, probabilistic machine learning and deep learning for engineering and business, is really a program of utmost importance in present days. We have a couple of programs continuously running in the leading domain of research and technology in these days. It is an initiative of Ministry of Electronics and IT, METI, who has sponsored this Electronics and ICT Academy. Initially, in the first phase, there was 7 academies were there, but now we are 15 academies all over India running such type of faculty development programs. And you can look at our MNIT Electronics and ICT Academy and then register in the program of your interest. So in this particular program, I am very delighted to know that many speakers are from IITs, NITs and industry persons, and the participants will be greatly getting benefited by interacting with such eminent pioneers of our country. In this particular program, along with the theories, there will be quizzes, there will be practical aspects also. So I request all the people to uh, go through the quizzes which are required for their certification, and the materials will be available in the Canvas platform also. So that will be also great help to all the participants. So with this, I congratulate the organizers for the starting of this particular event with large number of audience over here, and request all the audience to attend the sessions in a very effective manner. So I wish all the best for this successful FTP. Thank you.
Thank you so much, sir, for your valuable words and for inaugurating this FDP. Following the insightful word of our senior leadership, it is privileged to welcome another esteemed academician whose guidance continues to enrich MNIT research ecosystem, Professor Lava Bhargav, Dean RNC, MNIT Jaipur. Professor Bhargava holds a PhD in VLSI from IIT Delhi and brings over 30 years of academic and research experience. His expertise includes low power VLSI, FPGAs, embedded systems, IoT, and emerging technologies like memristors. With 35 plus publications, 8 research projects, and 12 PhD supervision, he exemplifies a strong commitment to interdisciplinary research. His consistent encouragement and belief in the power of capacity building have been instrumental in shaping initiatives like this FTP program. We are especially thankful to him for continuously inspiring effort that enhance the academic and professional growth of educators and research across the country. Most importantly, we are deeply grateful to our head of the Department of Management Studies, Dr. Devesh Kumar, whose constant encouragement and visionary leadership have played a key role in motivating the faculty members of DMS to organize this FDP. His unwavering support has laid a strong foundation for the program, and we sincerely thank him for enabling us to begin this academic journey on such a positive and purposeful note. Sir, we are privileged to have you here with us today. I now request Sir to kindly address the participants.
Good morning, everyone. And I think credit should be given where it is due. I do appreciate Dr. Sandeepan, Dr. Ayush, and Dr. Gunjan, Professor Rajesh for bringing up such important FDP. And I do see personally, basically, that if as a country we want to succeed and want to be a very tech-driven country, in that sense, we should also, it means most of the people in the country, they should have exposure to that machine learning and deep learning. And I feel very pride when I see the contribution of my department. It's the third in the series FDP that we are having under the that umbrella of EICT. And for that, we do that thank Professor Nayan Prasad Padi, Professor Vineet Sahula, Dr. Nanda, and we got lots of support from EICT, and that's why we are able to do that much. From the department point of view, we are a department where all these interdisciplinary type of that research should be happening. We are going ahead with this vision, and we also discuss among our faculty members that if we are going to work with the engineering or tech-based type of departments, we may be helping those departments in understanding the business application. Okay. And in that way, I do again congratulate Dr. Sandeepan, Dr. Ayush, Dr. Gunjan, Professor Rajesh for bringing up such an important FDP where we can understand its business application as well, and then only it is going to contribute towards the success of our country economically, and also we can improve our expertise in the similar context basically. Okay, I thank all the MNIT that officials basically, and also congratulate the faculty coordinators. Thank you very much.
Thank you very much, sir, for your thoughtful address. With the inspiring words from our esteemed leadership, we now turn to the core of the academic endeavor, the theme of our faculty development program, probabilistic machine learning and deep learning for engineering and business. As AI systems increasingly shape engineering and business decisions, the ability to model uncertainty through probabilistic approaches has become essential. This FTP aims to equip participants with both theoretical insights and practical tools to navigate this frontier. This vision has been brought to life under the able coordination of Dr. Sandeepan Karmakar, Assistant Professor in the Department of Management Studies, MNIT Jaipur. His commitment, planning, and academic leadership have been central to the successful organization of this program. It is now my pleasure to invite Dr. Sandeepan Karmakar, Assistant Professor of DMS MNIT Jaipur and coordinator of this FTP, to share an overview and key insight about the course structure, objectives, and the learning outcome we aim to achieve during the coming days. Dr. Sandeepan Karmakar is an assistant professor with a PhD in Industrial and Systems Engineering and an MTech in Industrial Engineering and Management from IIT Kharagpur. His core areas include inverse problems, compressed sensing, partially diagnosable system, Bayesian machine learning, and data mining. Dr. Sandeepan has played a pivotal role in conceptualizing and organizing this FDP, and we look forward to hear from him about what this program has in store for our participants. I now request Sir to kindly address the participants.
Sir, you're on mute.
Yeah. Oh, thank you. Thank you, Shinu. Thank you for this opportunity to express my feelings about this particular program. Since along, I was planning to actually bring all these kind of methodologies, all this kind of science, and all these new developments in this particular little bit lesser explored machine learning and deep learning area for engineering and business. My aim is to actually create the literacy of this particular this probabilistic MLTL to the academic as well as industry, so that they will be able to implement all these things in their real projects. Okay, so now the thing is that as we are talking about this probabilistic MLTL, so it is actually coming from conventional MLTL. So how it is actually different from this conventional MLTL? So basically. What happens that conventional MLTL, we are actually going by something called as frequentist approach of statistics. There are actually two schools of thoughts. Okay, whereas probabilistic MLTL, it is actually motivated by Bayesian statistics, Bayesian school of thought, where we are actually working with the probability distributions. These probability distributions, they are not directly brought in case of conventional MLTL. They are more of algebraic nature, and they are more of optimization based approach. Okay, so now why this particular probabilistic MLTL that is actually getting popular day by day? You might have heard, everybody knows about generative AI, but where this generative AI actually coming from? It is actually coming from this particular probabilistic MLTL. So we are actually stepping one step back, okay, to understand that what is the origin of this kind of generative AI. Now, this generative AI, I'm not going to cover, but we'll be giving some kind of hints towards the end of this particular program. So some success stories of Bayesian modeling, actually we can look at the very first successful application of Bayesian modeling or Bayesian analysis was in 1968 when one submarine, okay, US submarine that is known as Scorpion. So that Scorpion was actually moving from east coast to the west coast, and somewhere it got missing. Okay, so scientists were looking for its debris. So what happened to that particular submarine? then all were in vain. All kind of efforts were in vain. Okay, they had modern technologies that time, 1968. Okay, that time they had the best kind of technologies to find out that kind of that submarine, but all these efforts actually went in vain. Then some Bayesian statisticians, they actually came into this particular to find the wreckage of this particular ship, and they could find out in within 5 mile radius of Atlantic Ocean, they could actually find out. So this is what actually motivated this particular Bayesian modeling, and we'll uncover all this nitty gritty that how actually we can bring in this Bayesian modeling in our real life, and these are we are doing this kind of intuitive kind of inference and all these things every day, but knowingly, unknowingly. So we will be bringing it into our classroom. Okay, so now what are the factors behind this particular success of this particular probabilistic MLDL? That is, you can say the lots of data are now getting generated. Okay, and if you will be uncovering this detail when we'll be going into this probabilistic MLDL introduction and all these things, then we'll be finding that this probabilistic MLDL not only gives some kind of estimates, okay, they actually give some kind of bound of estimates, okay, and which is coming inherently in that particular approach, which is not available in conventional MLDL. Now, what are the hindrances of probabilistic MLDL? That is basically, first of all, mathematically, this is rigorous. Okay, so we have to accept that this is mathematically rigorous. Okay, but the thing is that once you understand that mathematics, my aim and objective is to make this particular mathematics to be understood by even a layman. Okay, so and it is very easy actually. It is very easy. There are so many notations, there are so many you can say complex things, but they are very easy at the center. Okay, so hindrances first is the mathematically rigorous, and second one is that we have to do long simulation of the mathematical models. Okay, to come out with an inference. Okay, so now this long simulation actually it takes computational load. Okay, so heavy computational load. So that's why basically this had become hindrances to this particular probabilistic MLDL. But now we are having storage devices, we are having computational power, we are having GPU with us. So many kind of efforts are being done that how to make the computation easier. Okay, so we'll be looking at this nitty-gritty of this particular probabilistic MLDL. Now, what are the topics covered? Topics will be covered. We have already, I have already sent you this particular list of topics that what we are going to be going to cover this particular program. And regarding the course logistics, this is very important. Okay, so everybody actually wants to know that what will I get. Okay, so what is the award I will get. So for the course logistics, basically, so first our teaching assistant will be Miss Renu Varghese. Okay, she will be helping us in carrying out all these kind of course logistics activities. Second is we'll be using Canvas as our learning management system. Third one is all the lectures and class materials will be shared. Okay, and most probably we'll be sharing YouTube links so that you don't have to download them in your hard drive, and you don't need to spend storage or use storage for this downloading and all these things, storing these things. Now, what are the evaluation components? So attendance must be at least 70%. Can you please keep on mute? Yeah. Acha. So first is attendance must be at least 70%, and which is the weight 50% weightage in the final evaluation. Then number of quizzes, there will be 5 quizzes. All 5 must be taken, and 3 based means all 5 must be taken by you, and 3 based out of 5 will be considered for final evaluation with score at least 60%. Okay, and you'll be getting 2 attempts for each of the quizzes. Okay, so you can actually refine your answers. So this is also here also this particular Bayesian methodology. I'll be discussing all these things later. Okay, that how you can actually update your knowledge, update your information, update your posterior information actually. So what is the weightage of this particular component? Quizzes will be in the final evaluation, that will be 30%. One assignment on preparing a report on an application of this particular probabilistic MLDL. Okay, so that is required. So you have to submit a report. Okay, and weightage in final evaluation is 20%, and a 60% or above overall score will be awarded a certificate. Okay, so this is about the evaluation components. Okay, so I'll be ending it here, and the first session will be taken by Professor Gunjan Soni sir. Okay, so he'll be introducing you to this particular statistical modeling. modeling, different distributions and all these things. Okay, and a little bit introduction on the Bayesian theorem, Bayes theorem, and that will be our center of everything in this particular probabilistic MLTM. Okay, so wish you happy learning. Okay, any kind of information you want, in any kind of problem you are facing, you please contact in that WhatsApp group. We'll be happy to help you. Okay, thank you. Thanks a lot. Over to you, Shinu.
Thank you, sir, for that comprehensive overview of the program. Your efforts and dedication in curating such a well-structured and impactful FDP are truly commendable. As we move towards the close of this inaugural session, it is now my pleasure to invite Dr. Ayush Gautam, Assistant Professor, Department of Management Studies, MNIT Jaipur, co-coordinator of this FDP, to deliver the vote of thanks. Dr. Ayush Gautam expertise lies in supply chain management, circular economy, and sustainable transportation. A former analytics specialist at Accenture and Newton Bhabha Fellow, he leads pioneering work in circular supply chain business model for waste management, showcasing his commitment to address global challenges. Dr. Ayush has been instrumental in planning and execution of the program, and we now request him to formally express our gratitude to all who made this event possible. Over to you, sir.
Thank you. Thank you very much, Shinu. Okay, thank you very much, Shinu. And I would like to thanks all the participants for showing your interest in this course. But I would like to start with the heartful thanks to our director, Professor N.P. Padi, and chairman of VICT Academy, uh, Professor Vinit Saula, the chief investigator, and Dr. Lava Bhargav, Professor Lava Bhargav, Dean RNC, and Dr. Nanda. I would also like to thank Dr. Divesh Kumar, HOD of Department Management Studies. Without his encouragement and his support, we are not able to float this kind of courses. And I also would like to thank Dr. Deepak Verma as a continuous mentor to us. And the thanks goes to Dr. Sandeepan Karmakar to come with such a very relevant and mathematical Bayesian statistics based course, which is highly relevant for the optimization and the AML market. And I would also like to thank Shinu for handling the courses, and most importantly to all the participants for showing interest in this course. So thank you everyone. And now I would like to invite Professor Gunjan Soni to start the lecture, as we already passed the 30 minutes. So I won't take much time. Gunjan sir, you may please start. Thank you. Thank you everyone for joining.
Thank you, Dr. Ayush, for the warm welcome. And I hope, Shinu, you have to coordinate. I should directly go to the lecture now.
Sir, I would like to give a brief introduction about you so that
Please give the brief introduction of Gunjan sir before
yes,
we start.
yes, so that a participant can connect with you. Okay.
Yeah.
Okay. Dr. Gunjan Soni is an associate professor in the Department of Mechanical Engineering. He earned his PhD in mechanical engineering from BETS Bellary in 2012 and completed his MTech in industrial engineering from IIT Delhi. His research interests include predictive maintenance, supply chain management, and application of AI in manufacturing systems. Sir will begin with a review of foundational concepts such as conditional and joint probability, various probability distribution and transformation. Additionally, he will cover a quick overview of frequentist deep learning, touching on architecture and optimization frameworks. Very glad to have you, sir. Sir, over to you.
Thanks, Shinu.
Thank you,
So, Professor Karmakar has already given a brief about why the Bayesian belief and probability has to be talked about. Yes, we have a lot of data. Yes, that data needs to be used. And yes, the dynamism of the environment needs to be captured. So there we go. We have Bayesian to the rescue. But before, my job over here is to just talk about the basics of probability, because you just can't jump onto a topic. So a primer, a little bit of intro needs to be given. So I'll stick to that job. And okay, many of you must already be having great idea about probability and have been discussing about it in your academics or in your research. It might look noise that we're talking about basics of probability, but there might be people who would need um, a bit of an introduction as well. So let's take it from a lighter side and then we progress towards the complexity. So I'm sharing my screen. It's showing if you're having problem connecting to sharing device. Just a second, I'm checking it again. I've just shared. Shinu, can you let me know if my screen is visible? There's an issue over here. So I think I'll switch to my laptop now. I was using desktop. Just give me a second.
Kunjan, you can use the WebEx app actually.
Okay, sir.
Web browser sometimes.
Yeah, I'm actually using my Google Drive only to share. I'll just try it again.
You
Just
can
sharing
download.
my screen now. Can't share content, it is saying. Anyway, so I mean, as and when required, I'll do that. But it might be good if we try it once more. It's not sharing screen. Somehow it's not able to do that. So,
Share some application, any app you can share.
yeah,
Maybe Word or something. Just try that.
actually, yeah. Also, I'll shift to my laptop. It's better then.
Geeta Ramesh, can you just see whether he has a right to present? Geeta Ramesh.
I'll anyway switch to slides but when it's required. Let's not waste time here. So yeah. So basics of probability is, I mean, we know that we talk about uh, the probability is a chance event or the chance that an uncertain event may happen, and we measure it between 0 and 1. There's a word like event which is often used, which is we say is the possible each possible outcome of an experiment. You can say an experiment, probably not in your day-to-day life. You may not call it an experiment, but if any activity is being done and there are multiple outcomes, we say there are several events which are possible. Simple event we say is an event that can be described by a single characteristic. We say sample space is another aspect of it. We say is collection of all those possible events. We say is the sample space. So three types of probability we generally talk about. First is the a priori classical probability. The second one is empirical classical probability, and the third one is the subjective probability. So a priori classical probability we say is where the events are already fixed and we already have prior knowledge about uh, the occurrence of those events, and we can just find out the probability of it. For example, tossing of a coin or rolling of a dice or taking out spade from a deck of cards. So all these are predetermined. Their sample space is well defined and it is well structured, and we already have the prior knowledge about it, the process which is involved in it. So that's a priori classical probability, and it's not too much useful at times in real life because first the sample space may not be discrete, like it's there in the a priori classical probability. Secondly, it's not possible to have greater knowledge about the whole the brackets, where to close the brackets. Yeah. So then you have the second one, which is empirical classical probability, where the probability of an event is based on the observed data, which is what Bayesian will also deal with mostly. Uh, what is the meaning of observed data is something you are capturing the data, and you may or may not be taking it dynamically. But then if you have captured a lot of data, past data, and there is a continuity in the scales, their scales are continuous. So empirical classical probability is the most used probability, or mostly practical um, probability. Most practical use of the probability is in the empirical one. And then you have the subjective probability, which is we do it on our day-to-day basis, where the probability of an event is determined by an individual. And like when we are overtaking from a car, or we are planning to reach somewhere on time, we are always doing that. So that is subjective probability. And now it is also very much related to the Bayesian part, because Bayesian is about how your beliefs are evolving with time. So similarly, there is a subjectivity involved, and Bayesian tries to capture that subjectivity. Uh, Subjective probability is largely experiential. I mean, you decide it on the basis of your experience. I mean, let's say you might be guessing that what's the time that the lecture gets completed. So you must be guessing, okay, around 5 minutes before or around that. So something like that. So we say it's the subjective probability from that aspect. But let's say if light goes in between, so that subjective probabilities, there's a possibility that it needs to be updated because the lecture needs to get completed. So then your estimate needs to get revised, right? So hence the Bayesian belief part comes in. Or there is a sunshine and you don't take umbrella with you, and then there are dark clouds coming in. So you update your in your belief, you update that okay, there's a possibility of rain now, I should take the umbrella. So that's what you say is subjective probability. And they actually Bayesian belief is actually updating, it's supplementing your subjective probability. It will be very interesting as the course progresses. So how do we calculate a priori probability? Because we already know the events which are occurring. So we know the number of ways in which the event can occur. Let's say what is the probability that you draw a red card? Red card 26 by 52, right? So because we already know the number of ways, number of red cards which are available, and the number of black cards which are available, and the total number of possible outcomes we already know. So we call it a priori classical probability, while empirical is about it's observation based. So number of favorable outcomes observed by the total number of outcomes observed. So you take a test, and out of 100, 10 students get marks greater than 90. So what is the probability a student gets 90? What is the probability that what is the probability of getting 90% is 10 by 100, so that makes it 0.1. So that's how you can say is the probability of occurrence can be calculated for empirical classical probability. So yeah, so some examples were there. I think we are also recovering on time, so I'll skip those. These were simple things. Events in sample space. So yeah, this will be nice. So give me 2 minutes. I'll just shift to my laptop and then share the presentations. Meanwhile, you can just ponder about Bayesian part. Just putting in the password and then logging in from the laptop. I'm sorry, there's an issue over here also as well that's not logging in. Meeting number is not getting recognized. So, I mean, the Murphy's Law is playing over here. So, anyway, so I'll not uh, waste time. I'll share the presentation later. So, anyway, uh, meanwhile, if I, Sandeepan sir, you are there?
Sir, Sandeepan sir is not here as.
Okay, Shinu, can you help me here? I'll send you the slides.
Okay, sir.
Just give me your email ID. I'll send you the slides. And
Okay.
then you can help me in changing the slides over there.
Okay, sir. Okay.
Yeah.
Okay. I would be texting over the chat.
Yeah.
Okay, sir.
Although the lecture can be taken, but it won't be fun anymore if just it's numbers and the tables. So it has to be. Yeah. Shinu, have you sent the email ID of yours?
So I'm sharing it.
Yeah.
1 second.
Yeah, generally we've been using Google Meet and other platforms, no WebEx. Somehow I'm not able to share. It's not allowing me to share. You may later on check with other people also if prior before the
Sir, I have
presentation.
shared the mail ID.
Yeah, good. Yeah, I've got it.
Okay, sir.
Yeah, I've sent. You must get it now. So you can share it. And I'll just tell you when to change the slide. You can change then.
Yes, sir.
Have you got it?
1 second, sir. We need to check. No, sir. 1 second.
Just refresh now, you'll get it. Yeah. Yeah, you must have got it now. It didn't bounce back.
Yes. No, sir. I haven't received it.
Okay, I'm sending it again. I don't know what's happening.
Sir, is the
Send-
email ID is 2024 RBM. Yes, 1 second. I got it. Got it.
Yeah, just
Okay. Okay.
so we lost another 5 minutes over here. You can go to slide 9 directly.
Visible, sir?
Yeah, that's so. You go to slide 9.
One second. This
Okay,
was
so yeah, so when we have, let's say, how do we break down a problem into its components? We use a contingency tables. So, for example, this is the simplest of the diagram which you see. We got full deck of 52 cards, and then the red and the black card, and then ace and not an ace. So, if we, let's say, we are working on probability of getting in black ace, something like that. So, we can break down the problem into its components. Although the problem is very small over here, but then contingency tables helps a lot in the situations where there is a tree structure, where there is a decision tree emanating out of it. So hence now you can go to the next slide. So we talk about simple and joint probability. So simple is you can also say is a marginal probability, where we refer to a simple event like probability of drawing a card, or probability of drawing out a red card, or probability of a king. But then if we so this is a simple event. Now if we go to two or more events, or a composite event, so where we say two different events happening together. So that is what is the probability of drawing a spade king. Okay, so that's where we say is the joint probability. There are a few other terms like mutually exclusive events. So these are the events that cannot occur together. So I think most of you must have read about it earlier, but then again, it's okay to think it from that point of view. In terms of a priori probability, if we talk about a queen of diamonds or a queen of clubs. So these two events are mutually exclusive. Okay. Uh, they are not when they're not talking about the color, so they become mutually exclusive. And if we start, if another example of simple, you can say mutually exclusive events could be a boy or a girl being born. So they are mutually exclusive. Uh, whether anything that's binary, anything that's the outcomes are pure, we say they are mutually exclusive events. Then we have collectively exhaustive events. Term called collectively exhaustive events are where one of the events must occur, and the set of events covers the entire sample space. So can you go to the next slide, next to next slide? Yeah, so you see here, collectively exhaustive events are those events which are not necessarily mutually exclusive, but when collected together, they complete the sample space. Like A is the aces, B is the black card, C is the diamonds, and D is the hearts. So if we collect all of them together, they'll make up the complete sample space. So we say they are collectively exhaustive. But at the same time, B, C, and D, because aces are black also, or diamonds also, and hearts also. So A, B, C, and D are collectively exhaustive, but not mutually exclusive, while B, C, D are mutually exclusive. So this is some clarity which was required. Then we can talk about the marginal probabilities. Can you go to the next slide now? So when we are talking about composite events, probability of A and B happening together, where we say is the number of outcomes satisfying A and B, of course, as you know, and the total number of elementary outcomes which are there. So elementary outcomes means the individual events, probability of individual events happening. So when we are computing a marginal or a simple probability, we have to take care that marginal probability of A. So so A basically is an event where which can occur with different events of another set. So here we consider OR, that is probability A and B1 happening, or probability of A and B2 happening, or another, all these mutually exclusive events. And then that's how we are defining the marginal probability over here. So we take an example. Can you go to the next slide now? So taking on from there, so probability that you draw a card which is red and is ace as well. So you say the number of cards. I mean, we are still using the a priori because a priori is easier to explain and easier to understand. So that's why we generally take examples of a priority probabilities. So number of cards that are red and ace are 2, and the total number of cards is 52. So how do we look at it? So this is how you can see where is it located in the table, in the contingency table. Now we go to the next slide where we talk about the marginal probability of ace. So can you go to the next slide now? So probability of getting an ace. So now ace can happen in red and black both, right? So hence 2 by 52 and again 2 by 52, we make it 4 by 2. So although it can be directly calculated without making a contingency table as well. But then the idea over here is to how to organize the data and break it into parts so that you can find out the marginal probability. So this is the way we can do it. Then if we have to calculate the joint probability from the contingency table, how do we do that? Can you go to the next? Yeah. So here what we have is now we can label it the inside the cells. All the items which are there inside the cell are, you can say, the joint probabilities, while the rows and the columns at the end we say are arranged in for the marginal or the simple probabilities. Right. So this is a simple structure, and it is very useful in or if there are multiple outcomes emanating, and if you have to make a decision tree, contingency table is very useful in that case. Can you go to the next slide now? So till now, what we have talked about is the probability, the numerical measure of the likelihood of an event happening. It lies between 0 and 1, and mutually exclusive events. The sum of probability of all mutually and collectively exhaustive events is 1. So generally, we say that we sum up the probabilities of the events happening in a set, and it should sum to be 1. But only for mutually exclusive and collectively exhaustive events. So this is something which needs to be clarified. We can go to the next slide. So, yeah, next slide, please. Yeah. So there is a general addition rule which we follow, that probability of event A or B happening, but that is probability of event A, their marginal probabilities minus P, A and B. So, or if it is the other way around, if you want to find out probability of event A and B happening together, you take the intersection point intersection part on the right side and take it the other part on the left. Then if they are mutually exclusive, then of course A and B can't happen together. So PA and B happening together is 0. So the rule becomes simplified then in that case. This is for mutually exclusive events. That's the formula we use for the mutually exclusive events. This is a we call this general addition rule. Let's say the implementation of this part in the next slide. So, what's the probability of selecting a male or a statistic student from population described in the following table? So, again, so this is an empirical data, and the male students who are taking statistics is given, male students who are not taking statistics is given. So, what we want to find out the probability that subject is selected by a male or a statistic student. So that's how we define it. The marginal probabilities are given over here. So 229 is your male, and students choosing for statistics is given as 160. So, and the intersection part male and taken statistics is 84. So hence we get this number. So again, you can see that contingency table is simplifying a lot of things that way. Can we go to the next one? Then we come to the conditional probability that what is the probability of event happening, A event happening given that B has already happened. So generally we come across the conditional probability part a lot in day-to-day life where uh, what is the probability that a student is going to enter into a class on time. Now that depends on the teacher also. If the teacher is very strict about the attendance and would not give 1 minute extra, the probability of entering of the student in the class will be higher as compared to the one who's relaxed a bit and may give attendance even if you are entering 5 or 10 minutes late. So that probability would be different. So the event that is you can say is probability of a student entering into a class on time would change depending on what type of teacher is there in the class. So hence we say the conditional probability which is coming into play over here. That's how we find it. You can see on the screen that the conditional probability of A given that B has occurred, and similarly for the other one. So A and B are the joint probabilities which we can get from the contingency table, and P and the A and B, PA, PB are the marginal probabilities. So can I give you a question to do so that you remain interested? Let's say I give you 2-3 minutes. Can we go to the next slide, please now? Yeah, so I would suggest you to make a small contingency table for this problem and try to work out this one. Anyway, you can work it out directly also, but just give you 2 minutes. I mean, let's say just to give you a wake up call in case you are feeling bored. Okay, anyone who's tried it? You can just post your answer in the group. Okay, anyone? Okay, Ankita is done. So let's see, Ankita, whether you're right or wrong. Anyone else Who's done that? Okay, Siddharth seems to be the closest one. Good. So yeah. So let's see the answer now. Can we go to the next slide? So let's see. You make this contingency table. We have it's something like the used car. I mean, air conditioning is there or not, and then the CD player is there. Of course, the CD players are not there anymore, but then you can say its console is there or not. So CD players, the probabilities having both. So it's given that AC and CD, the joint probability is given as 0.2 over here. And of course, it's also given that 70% have air conditioning. So that's given over here is 0.7. And then no AC is given as, and 20% of cars have both, and 40% have CD player. So I think that makes it. And if once you know the marginal probability, you can find out the joint probability. Like here, if you know the marginal probability 0.2 and the total probability was known as 0.7. So I can find out the joint probability that the is having air conditioner but no CD player. So that's how I make this contingency table complete. And once I make that complete, I can clearly find out what is the probability of having a CD player given that there's an AC, given that the AC is there. So we can just find out the joint probability of it, and then we use it the way conditional probability formula to get this answer. So I hope you found it interesting, because generally at the first go, this kind of mistake do happen. But if you make the contingency table, we generally get it right. We can also represent it with the decision trees. Can you go to the next slide? Yeah. So this is another way of representing this, the conditional probability with the decision trees. This is also very relaxing, and I mean, it gives you sort of a complete picture, and it plays a greater role in Bayesian statistics. So that's how you can break the problem into multiple parts, and at the end you want, at the end of the tree, you want the joint probabilities for all the possible outcomes. Okay, so we can go to the next slide now. And one more after that. Go to the statistical independence. Yeah. So two events are independent if and only if probability of event A happening given that B happens is same as probability of event A. That basically means that A and B are independent of each other. It's something like probability of getting a heads given that it's cloudy today. So they are sort of independent events, and there is no link between them. There is no physics which is governing the turning up of heads or tails depending on I mean, that's governing the heads or tails. Yeah. I mean, the clouds are there or not. So we can say it like that. So events here A and B are independent, and this changes the way we treat the conditional probability. Can you go to the next slide, please, now? So we see here the conditional probability getting modified. Multiplication rule for two events. This is anyway coming out from the conditional probability formula only. But if they are independent, because A and B don't happen together. So that's how it's, and then the multiplication rule will simplify in this manner, which is given here at the bottom is event A and B happening is probability of event A happening and probability of event B happening. So multiplication of the marginal probabilities straight away. So yeah, we can another simple example of it. Can we go to the Bayes theorem that is next slide? So Bayes theorem is used to revise previously calculated probabilities based on new information. So here we start the part where we say is it's a sort of extension of conditional probability only. So go to the next slide, please. So here you see this part was anyway there. So BI is the ith event of K mutually exclusive and collectively exhaustive events. So one thing we have to be clear about the using of the Bayes theorem is that the uh, the event B which we are saying, the event B for which we want to find out the conditional probability, uh, it should be made up of collectively exhaustive events, and A is a new event that might impact BI. So this is the simple formula which we have. And if you look at the denominator, what has changed in the denominator is the simple conditional probability formula, there was supposed to be marginal probability. And if we still go further, the marginal probability, how we used to calculate marginal probability for um, multiple elementary outcomes. So if we look at that, it's the simple substitution. The marginal probability which was there earlier has been substituted with the collection of mutually exclusive and collectively exhaustive events. So this is some, you can say, development from the previous slides we see over here. You may not have to just learn the formula. It's the simple logic which is going on over here. Okay, so we can go ahead to the next slide. So let's apply the Bayes theorem over here. So a drilling company has estimated 40% chance of striking oil for the new well. Detailed tests have been scheduled for more information. Historically, 60% of successful wells have detailed tests and 20% unsuccessful wells have detailed tests. Given that this well has been scheduled for a detailed test. Now you see there has been a development in this that the well is scheduled for a detailed test now. So what is the probability that the well will be successful? Okay, so from the light of what we have discussed till now, from the light of the Bayes theorem that we have discussed in the previous slide, can you try to solve this problem? So I'll give you a few minutes to do this. You can say probability S as the is a successful well and U is U to be unsuccessful well, and then you can calculate the prior probabilities. Prior probabilities are actually given over here. Historically, 60% of successful wells have detailed test. And also it is given that 40% chance of striking a oil, that is successful. So 40% is like 0.4 success, and of course 0.6 would be unsuccessful. And some information about the joint probability, not the joint, but the conditional probability is given. Let's see if you can work it out. Yes, anyone? Good, Siddharth. Siddharth is following it very well. Anyone else? Dharmesh? Good. So, yes, a few people have been able to do this. Can we go to the next slide now? So, for the people who are trying, you can try. I'll share the slides later. You can try it again. So we define S as successful well, U is the unsuccessful well, and the prior probabilities are given over here. And we want to be defined detailed test as D. So probability that a detailed test is done for a successful well is 0.6, which was given. And these are the other two conditional probabilities which were given. We go to the next slide now. So we apply the Bayes theorem over here. Given this, from this we get 0.67. Okay. Can we go to the next slide? Yeah. So now there was a primer to Bayesian theorem which we've given. Now we can talk about some probability distributions. But before we go ahead, we have to define a term called random variable. Now, random variable from the term is sort of a misnomer. Random says that anything can happen. And random variable is something which is changing. So is it really random? It's basically it's not random from the definition point of view. It's random in a given pattern. It can take any value in those certain defined limits. So randomly it can take any value following a pattern in the defined limits. Then we say it's a random variable. Now, everything where we look around, we see uncertainty, and it's how do I specify that uncertainty is using the random variable. That random variable is we capture it and would like to do some prediction for that random variable. It could be anything. It could be the share market. It could be the weather. It could be the speed of the car. It could be marks. It could be anything. So most of our life, we are not fixated on the deterministic values. Largely, it is governed by the numbers which can take some value in a given range, and we move through those numbers. So hence the term random variable is coming into play. And hence we are getting the term distribution, that what is this pattern of this random variable, right? Then we talk about what nature of the random variable do we see. So is it discrete or is it continuous? So we look towards the random number from two different perspectives. That is whether the random number is a discrete, not random number, random variable. It's a discrete random variable or a continuous random variable. So let's go ahead. Go to the next slide, please. So random variable is a possible numeric value for an uncertain event. And I've already talked about it's a misnomer. It's not actually random. Random that can take any value. No, it can't take any value, but it can take any value for a given pattern, which will follow certain pattern and in a given range. So discrete random variable produces outcomes that come from a counting process, that is number of items. So discrete, I think you know that. What's the meaning of discrete? So here one thing needs to be clarified is the random variable. We say it is discrete because the outcomes are coming from a counting process. That's why we say it is a discrete one. And in that continuous one, the outcomes are coming from a measurement. So counting and measurement two are different things. So that's how we generally would try to differentiate between the two. If the outcomes are coming from a counting process, it's a discrete random variable. If the outcomes, if the random variable which is producing the outcome, those outcomes are continuous in nature, we say it's a continuous random variable. So we can go to the next slide now. So this is one cliched example of rolling of a dice, which where it's clearly visible, evident that the outcomes are discrete in nature, hence the random variable associated is discrete. So rolling a dice, if we are doing it a number of times, or tossing a coin a number of times. Go to the next slide, please. So you got these random variables. I generally use these slides in my classes, so hence the chapter numbers. So this we talk about two different random variables. We go to the next one now. Next slide, please. So probability distribution for a discrete random variable, where you see the number of classes taken. So this is a distribution. That is the pattern, right? So number of classes taken to the probability is 0.2. Number of classes in a week, the number of classes taken. This is a distribution for the number of classes taken in a given week. So 2 classes taken, 3 classes taken, 4 and 5 classes taken, the probability distribution is given here. So if we, let's say, another, go to the next slide, please. So another way of looking at it is also that if a priori, we have the a priori probabilities, how can I make the probability distribution? So probability, if we are tossing 2 coins, and let's say X is defining the number of heads. So what is the probability of getting 0 head in 2 toss of coins? 1/4. Here the sample space is having, heads, tails, heads, head, tails. So hence the sample space is having 4 possible outcomes. Hence we get this probability, and the distribution looks like this. So this is the probability distribution for a experiment of tossing of 2 coins. We go to the next slide, please now. So we can do few things about it. What is the expected value of this particular experiment, where tossing of 2 coins? So hence summation xpx we say is x is the number of heads which we are saying in this case, and px is the probability of that outcome. So expected value is 1 over here. Can you go to the next slide? Similarly, for the classes taken also, we can calculate the expected value, because it's sort of a mean. It gives us the middle of an uncertain set of events, the middle value. Of course, it is a representation of the average. Then we go to the next one, where if we are talking about average, we can't just leave the variance also. So can you go to the next slide now? So how do we calculate the variance of this? That's how we calculate the variance. Yeah, I think it's self-explanatory. So go to the next slide, please. You can just try it later. Now there's another term which is coming after. Can you go to the next slide after that? Yeah. Now we are coming to the covariance part. So this is very interesting. 2 variables which are varying together. When the x is varying, random variable x is varying, random variable y is varying, and together also they cause a phenomena which is covariance. It has units while the correlation does not have units. Correlation also correlation is fixed between -1 and 1, while there are no limits for covariance. It can go to any magnitude in either direction. Can we go to the next slide? So we will take an example to understand how the relevance of the covariance. So there's a formula for covariance, where generally correlation can be found out for multiple variables together. Covariance is limited to two variable comparison. So it happens in the pairs. Let's take a simple example. Go to the next slide, please. Yeah, so this was observed in India versus Pakistan match, October 23, 22, T20 World Cup match. So here you see that it was in the Diwali time, and I mean it was the peak of the shopping season for Diwali. And you can see on the x-axis we have the change in UPI transactions. So you see that it's on the higher side. Change in, I mean, the high Diwali shopping was happening from 9 to 1 p.m. Diwali shopping was there. The match was starting at 1:30. So right down there, the change in the UPI transactions fell drastically down, and it was on the negative side. I mean, it was reducing while the Pakistan was batting. And then again, Indian batting came, and it again fell down to a very low level in the last overs of the Indian batting. That shows now here what you observe is that how change in transitions is varying with the time. So two random variables over there. One random variable is change in UPI transitions, and another random variable over here is the the batting of the, you can say, the ace batsman of India. So as he was scoring higher, the change in transitions were more on the negative side. So these are two independent variables in, if you look at it from a macro point of view. But if you look at it together, you would find that they are co-varying, right? So that's the interesting aspect of the covariance. Can we go to the next slide now? So here you would see that the most of the applications of covariance are in designing the portfolios. So you see that there is a passive fund and there is an aggressive fund, and economic condition is given. So if it's a recession, and if it's a stable economy, if it's an expanding economy, their investment values are given. Okay, so consider the return per $1,000 for two types of the investments. So you can say when it goes in recession, and passive fund is X and aggressive fund is Y. So their covariance is coming out as 0.2. Then you would say it's a recession. And when passive fund is $50 and then aggressive fund is $60, it may indicate a stable economy, and the covariance value is coming out as 0.3. So how is this information useful? Can we go to the next slide now? So what can be expected? Like what returns can be expected over here? So if we multiply the covariance values with the corresponding values of the investment of for X and Y, we get the expected values. Okay, so here what's happening is that it is helping the person in identifying the possibility of returns given the situation, whether it's a recession or stable economy or an expanding economy. So here we can say that fund X is averaging and the fund Y is averaging this much for investment. Another thing which we can observe over here is, can we go to the next slide? Yeah, so if we can find out the variance, the standard deviation also from this one, we get this value, these values, and then we can interpret that fund Y as a higher average return and is subjected to more variability then the probability of loss is higher in this case. So because now 193.97 is a very high variability, although it looks like it's giving a return of $95, but it is higher. And then can you go to the next slide? And then we go to this way covariance value XY, where 8250. So this is again very large value if we look at the individual variance. No, if X and Y, if we look at sigma X and sigma Y individually, they were smaller. One was 43.3 and another one was 193.71, but together they are varying a lot. So since covariance is large and positive, there is a positive relationship between the two investment funds. So, and this is a very strong positive relationship, you can say, that they will likely to rise and fall together. So this will this type of interpretation can also help us in identifying whether I should be investing in a portfolio. I should be making a portfolio where they don't act. I mean, it might be a different choice for you, but for I would like to have a balanced portfolio where if X is doing bad, then Y should do good. So that averaging out is there. But if one is doing good and another one is also doing good, so there is a possibility in the bad times they both are going to do very good and they might take the average down. So that's one interpretation you can get from the covariance which we are finding, that if they are highly covarying together, it's not a very good option to put these kind of funds in a same kitty. So can we go to the next slide? Yeah, so these are some terms which we have came across. And if there are multiple variables, the expected value of the two random variables can be calculated in this way. And for the variance, the formula is different. That's how we do the formula. That's how we calculate the variance for two different random variables together, a composite event, if we say. And now we can talk about the continuous one more distribution, that is binomial distribution. Can you go to the next slide? So binomial distribution is a collection of Bernoulli trials. Bernoulli trials is like tossing a coin. But if you are doing it multiple times, then we say it becomes a binomial, it exhibits binomial distribution. So again, two mutually exclusive and collectively exhaustive events, at least one event will occur. For example, you can say head or tail in or defective or a not defective. So which is very much useful in the quality control, or having a boy or a girl, success or a failure. All these are events. They're binary in nature, and so we can go ahead and talk about this. Can you go to the next slide? So here observations are independent. That is, the tossing of one coin is independent of the tossing of the another coin. The outcome of one observation is not affecting the outcome of the other. And how you can sample multiple, how can you take out the observations is either you do it for finite population with replacement or infinite population without replacement. That's how you can do this. Can you go to the next slide? So the applications of the binomial distribution are like it's used in manufacturing plant for quality control. It's for bidding contracts, whether you get a contract or not. It could be winning elections, yes and no. You getting a job offer or not, or losing and gaining, or losing or winning. Yeah, so you see the applications are wide for a binomial distribution, and of course it can be approximated with a continuous distribution as well. But we'll see that later if the time permits. Can you go to the next slide now? So yeah, next slide, please. So that's how we do that. I mean, next slide. Yeah. So we use a combinatorial approach to calculate the number of combinations, or if you find out the sample space for the events. So hence we use this formula NCX. So we can go to the next one. Next slide. So this is the probability distribution function for a binomial distribution, where n is the number of trials and x is the number of successes, and p is the probability of an event happening. Or you can say success. That's how we do the calculation for binomial distribution. For calculating the yeah, go to the next slide, please. So what is the probability of one success in 5 observations? The simple exhibit is there. So we can just substitute these values, and I hope you would be knowing how to do the factorial calculation. So hence we go ahead. Please go next slide and next slide. So with two different binomial distributions where the sample space is same, but the probability of success is different in both the cases. How it is changing, the pattern is changing. The random variable is going to act in a different way in both the cases over here. Yes, next slide. So we generally use binomial tables for that, and of course, you can explore this part later if in case you have not. If you find it interesting, we can connect later. Go to next slide, please. So the characteristics of binomial distribution, mean and the standard deviation, is by these formulas, of course. So go to the next slide. Go to the next. Now we talk about another type of discrete probability distribution, which is Poisson distribution. Poisson distribution is again used in places where the area of opportunity is continuous unit. Area of opportunity, how do I define? Let's say we want to know that a cloth. So a cloth coming out of a mill is, if we consider it to be a continuous product. So if we have to say that what is the probability of observing blemishes on a piece of cloth. So that's somewhat vague. So if here we need to define the area of opportunity, or if we are saying that in a population, what is the probability of a disease? What is the probability that a person is suffering from a flu? So the population is very large, and the area opportunity needs to be defined, let's say in a given square kilometer, or I mean, you have to define area, then only you will be able to work it out. So here in the Poisson distribution, we have a term called area of opportunity, where then we can talk about number of scratches in a car's paint. or number of mosquito bites on a person, number of computer crashes in a day. So these are some of the aspects where the generally happens where the sample space is pretty large and the probability of event happening is very small. Can you go to the next one? So here we say we wish to count the number of times an event occurs in a given area of opportunity. Then as I've already said that the probability that two or more events occur in a given year approaches zero as the area of opportunity becomes smaller. So the applicability of Poisson process is largely where the probability of event happening is very small. So hence you say these kind of things happen. And we define a term called lambda, which is the average number of events per unit. You can go to the next slide. And the PDF probability distribution function for Poisson distribution is given over here. And we can go to the next slide, please. Now, although it has been applied for a very small problem over here with the for 5 cars entering a parking lot per minute. So again, the area of opportunity here has been defined as a per minute because in a given day, number of cars entering or leaving a parking lot would be pretty much higher. So hence we have to fix it on a minute basis. So we can calculate it like this. Okay, so you can just browse through the slides for next 2-3 slides. Yeah. So next, similarly, the shape we get for different value of the parameters. We go to the next one. Now we have the normal distribution, which is we also say is the mother of all the distributions. So it's a continuous distribution, continuous probability distribution, and the outcomes which are coming, the outcomes of the normal distribution are continuous in nature, like the thickness of an item, the measurement items. Thickness is measured, time is measured, temperature is measured, height is measured. So potentially they can take any value in a given range. Hence we keep the normal distribution in the category of a continuous distribution. So some of the properties of normal distribution we can talk. Can you go ahead? So it's a symmetrical curve. It is asymptotic to the x-axis. That is, it never touches the x-axis. On the left and the right side, it is symmetrical. Mean, median, and mode are equal in for a perfect normal distribution. And the spread is characterized by the standard deviation. So that's how we define, that's how we present a normal distribution. Can you go to the next slide, please? Now look at this formula of the probability distribution formula for a normal distribution. It is sort of very complex. Generally, if I have to find out for different values, if let's say I want to find out what is the probability that x equal to 1 or 2, let's say what is the probability for x equal to 2 for sigma equal to 0.2 and mu equal to 8. So can anyone tell me what will be that value? The hint is that you don't have to actually calculate. If I say px, what is the probability that x equal to 2, given that mean is 8 and standard deviation is 2? Anyone? I'm sure it's not easy to calculate, but you can substitute the value and get it, right? It will give you the value. But let me ask you another question. Let's say between 0 and 1, how many numbers are there? There are infinite numbers between 0 and 1, right? So if I ask you what is the probability of getting any number between 0 and 1, using the empirical approach, how do I find out? Tot possibility of getting that outcome divided by total sample space. So the 1 divided by infinite, then in that case. So that makes it 0. So hence for a continuous distribution, point probability is 0. This is one aspect which just for your information you can have, because if you put this in Excel or any computational for any computation, it will give you the value, but conceptually it is actually 0. Now let's come to this point where if I have to find out area between the curve, why would I find out area between the curve? What is a, let's say I have a probability distribution of the height of the students in my class, and if I ask if I want to, and I have the mean and the standard deviation for the distribution of the height, and I see that the height is normally distributed, which we have actually checked in the class, and generally height of the population is normally distributed. So why it's called mother of all the distributions is another aspect, but you can always say because of the virtue of central limit theorem, it turns out that this is the mother of all the distributions. Maybe it will be covered later on. So if we say that I have to find out if I have to find what is the probability that the height of a student lies between 155 to 160 centimeters. So I may have to integrate this function with the lower limit as between the lower limit of 155 and the upper limit as 160. But if when I'm going to integrate it, the integration of this function will be very difficult, which is not easy. So hence, people and the scientists have devised a standard normal distribution where they map the normal distribution to a standard normal distribution, and you can actually find out the value using the tables. You don't have to do the manual calculations. Can you go ahead, please? So this is the general parameters which you see. Can you go ahead now? Yeah, so these are some characteristics of normal distribution only. The changing sigma increase or decrease the spread. Of course, it's like a rope which is there hanging from thread or a nail, and then if you pull the rope up and down, the standard deviation, if it comes closer, the standard deviation gets lesser, and if it spreads far, then standard deviation increases. Can you go to the next slide now? So we have another term which is standard normal distribution. Because I've just told you that the integration of that function is very difficult by hand. So hence what scientists have done is they have devised a simpler way of calculating the function value by standard normal distribution, by making a table, standard normal distribution table, where Z is a standard normal variate, and they can calculate the value using that table. You might have seen that table anyway. So can you go to the next slide? Next slide. Yeah. Yeah. So the previous one, sorry. Yeah. So here, this is a standard normal variate, and we replace the x on the x-axis of the curve by z, and the fx will be replaced by fz. Go to the next slide. So this is the fz, and this is easier to calculate. Go to the next slide, please. Yeah, so it's also called a Z distribution, hence, where the mean is 0 and the standard deviation is 1. Now you can see that the normal distribution which you had earlier, where y-axis was fx and x-axis was x, it gets replaced by standard normal variate z and fz. The mean is 0 for this one. Go to the next slide, please. So it's a simple calculation which has been shown over here. But if I want to calculate a value of f for z equal to 2, it will be 0. Just remember, conceptually it is 0. Go to the next slide, please. So we say the distribution is the same, only the scale has changed over here. So 100 has been converted, x was 100 earlier, it has been converted to 0, that the mean is converted to 0, and subsequently other values are also converted to z. Go to the next slide now. So I think we finish over here with the normal distribution. If you have any doubts, do let me know. This is mostly the intro part of the what you'll be discussing later on. So yeah, anyone has to ask anything or say anything, can talk. So Shino, that's it from my side. Yeah, I've completed the slides. Also, the distributions which we have covered are uniform. I mean, uniform distribution is something which I had left. So because the normal distribution is the most important one, and exponential is there, but I just don't want to overburden you with many things which are there. So, yes. Meanwhile, I may ask. So if you can, let's say, find out for a small problem, like, can you, Shinu, can you go to slide number 91? Can you go to slide number 91? Yeah. So let's say this problem is there. So we have to find out the probability of x less than 8.6 for a given mean and the standard deviation 5. Can you use a normal distribution table to do this calculation? In case you don't know normal distribution table, we may have to actually see. Let me see if I can show you a normal distribution table and help you in solving this problem, because we have few minutes and I didn't see any question coming in.
Sir, can I ask a question?
Yeah.
Yeah. So the thing is, ideally, what we do is we move from binomial distribution to Poisson distribution, and then we can jump to normal distribution, like just by playing with the sample size and playing with the derivations of the distribution. So is it always like, is it all this relationship always holds, or is there some particular scenarios when we can move from binomial to Bernoulli, Bernoulli to Poisson, and Poisson to normal distribution, like
No,
derivation?
they are actually very independent. Bernoulli to binomial is yes, there is a link. Poisson is absolutely different from the binomial one. And normal distribution, binomial actually gets approximated to normal distribution because of the virtue of center limit theorem at times.
Okay,
But then
sir.
normal distribution is mother of all the distributions, because when you do sampling, if let's say you are taking out 10 different samples and then you find out the average of those samples, and if you plot those averages, it turns out that they are going to follow the normal distribution, be it any distribution, be it a normal, be it a viable for any parameter of viable distribution or a Poisson distribution, any distribution in the world, their averages, if you plot, will follow a normal distribution. So that's why normal distribution is so important, but there's no progression. Yeah, for binomial, there's a progression, and the condition is that the n into p should be greater than some 0.05, so that you can use approximate it with the normal distribution. Okay, so yeah.
Sir, one more question, sir. May I, sir, ask you to navigate to the India-Pakistan match problem that you graph problem that you show?
Yeah. Can you go back, please? Covariance. Yeah.
Yes,
Please
sir.
go back to the covariance. Yeah. Next one.
Yes, sir. Exactly. Sir, may I ask that what does this left axis signify? 22.5, 15, and 7.5. What does this left axis signify?
Change in UPI transactions.
Okay, sir. So if the change in the UPI transactions is going on, so whenever these yellow graphs are always visible, there are positive transactions. But
Yeah.
what does these green bars and the blue bars in negative they actually signify? How can we give a transaction in negative, sir?
See, actually,
And
let's say you set an average
okay,
transactions. Yeah, let's say the
okay,
average transactions in a given area you set. So that has
okay,
been that datum you set as 0.
okay,
Above the average and below the average, you can say.
okay. Above the average and below the average. So these are the average values. Okay.
No, I
So
mean the
same.
datum is set at 0. The 0
Okay,
is
data
at
set
the
at zero.
average. Yeah, 0 is at the
Okay, okay,
average.
okay. So same can be followed in all the kind of probabilities that we are going to set
Yeah,
up.
exactly. Yeah.
Okay, okay.
You can
Thank
you
you so much.
can you can scale it like that.
Okay, sir. Thanks.
Okay, so I complete my lecture over here, and I think the next lecture would be starting soon, as per the schedule.
Thank you so much, sir.
Sure.
Okay. So our next session would be starting from 11:15. You would be having 15 minutes break.